After the discovery of the electron by Thomson and the nucleus by Rutherford, there were a lot of scientists that believed that we had discovered all there was to know about the atom. But Niels Bohr was not convinced, and he did a lot of experimentation, and he found that those electrons, what he believed those electrons, or how he believed those electrons to be positioned, were not just haphazardly strewn around the nucleus, but were located in very specific energy levels that he could predict mathematically, at least for hydrogen. When objects are heated up to very high temperatures, they can glow or give off radiation. And when we allow just a single element to do that, it gives off, of course, energy, because we have put energy into that substance. When we do that, it causes the electrons in that substance to become excited, and they hop to higher energy levels. When they hop back down, they give off energy. Now, that energy is not just a continuous spectrum, but it occurs in, you'll see lines on an atomic emission spectrum when that happens. Those lines represent a hop between energy levels, what we might call a quantum leap between energy levels. And when those electrons hop down and give energy off, that energy is at a very specific wavelength, and we can measure that. And when we look at it in an atomic emission spectrum, we can see each of those energy hops as a line. Now, when we look at the hydrogen atom, if we look at this diagram, what this represents, now what you have to think about is that the nucleus is way down here, okay? So here's going to be our nucleus way down here. Here's our first energy level right here, going on up, and notice something very important about the energy levels. As you move away from the nucleus, and keep in mind that this is out of the atom up here, as you move higher and higher in energy levels, the distance between the energy levels gets smaller and smaller. So you have a large leap here from 1 to 2, a smaller leap from 2 to 3, and progressively smaller as we move on up away from the nucleus. The lines that we see appearing then represent hops between these energy levels. You'll notice these energy levels have arrows that point both out away from the nucleus and down towards the nucleus. And what that represents is, if anyone asks you to draw emission lines, if you're talking about atomic emission spectrum, you're going to be looking at the atom giving off energy. Therefore, that must mean that the electrons are hopping down to lower energy levels. So when, again, an electron hops down, that's emission. When an electron hops up, that's absorption of energy. So it's very important that you get the arrow going in the right direction. And for instance, hydrogen, we can, for its one electron, if asked, draw the possible hops between these energy levels. And the ones that we're most concerned about in the AP world are all of the hops that occur either from or down to the first energy level, the second energy level, and the third energy level. And if you'll notice, this area right here, all of the hops down to the first energy level, those are called the Lyman series. The next series here are all the hops down to the second energy level. That's called the Balmer series. And the other series that we're expected to be familiar with is the Cauchy series, and that's all of the electron hops down to their third energy level. So we need to know what energy level that they're hopping down to, what that particular series is called, and we need to know what region of the electromagnetic spectrum it's in. And a sentence students made up a long time ago. If you've ever had a urinary tract infection, they give you medicine and it makes you have very funny colored urine. And a student a long time ago made this sentence up, and I thought it was the stupidest thing I ever heard, but it stuck. My students still remember it when I see them in later years, and I'm still using it. I pee very blue urine lately. And you can pause this and write those words in. I pee very blue urine lately for each one of these letters. And that's to help us remember, counting down 3, 2, 1, this information, that all of the hops down to the third energy level are the Paschen series, and they are in the infrared range. So you might want to stop, pause, and put that information down. Again, all of the hops down to the third energy level, which you see that right here, are the Paschen series, and they are in the infrared range. When we look at this in class, we see the ones that we see whenever we look through our spectrum glasses and look at hydrogen glowing. We see the Balmer series, this series right here. This stands for the fact that all of the hops down to 2, and that would be these, all of the hops down to the second energy level are the Balmer series, and they are in the visible range. So pause again and make sure you've got that information down. All of the hops down to the second energy level for those electrons are called the Balmer series, and the radiation we would actually be able to see for this series. It's the only series that we can see because it's in the visible spectrum. Finally, the other one we're responsible for, the UL part with a 1, stands for the fact that all of the hops down to the first energy level, and that's these, are called the Lyman series, and they are in the ultraviolet range. So again, pause. All of them, hopefully you wrote that information down. A reminder again that first energy level, hops down to the first energy level, are the Lyman series, and they're in the ultraviolet range. So it's important to remember that information. So I pee very blue urine lately will hopefully help you remember that. Scientists by the name of Rydberg found that the wavelength of these lines, representing a hop from a higher energy level to a lower energy level, could be predicted using this equation. It's called the Rydberg Equation. 1 over wavelength. And I'm telling you, this is the bane of the existence of a lot of my students because they get the answer in the end, forget to get the reciprocal, and it's wrong. But 1 over the wavelength is equal to R, which is Rydberg's constant, times the quantity of 1 over the final energy level squared minus 1 over the initial energy level squared. So what does that mean? Or how does that play out in a problem? Well, look at the example. What wavelength of light in nanometers is produced when an electron in the hydrogen atom hops from the 4th energy level to the 2nd energy level? So our equation, since it's asking us for wavelength, 1 over the wavelength is equal to R, Rydberg's constant, times 1 over the final energy level squared minus 1 over the initial energy level squared. So 1 over wavelength is 1.09737 times 10 to the 7th reciprocal meters. The final energy level, remember, it's hopping from 4 to 2. So the final energy level is 2, so it's going to be 1 over 2 squared minus the initial energy level, which was 4, 1 over 4 squared. when we work this out, Rydberg's constant times 1 over 4 minus 1 over 16, we end up with 1 over wavelength being equal to 2.058 times 10 to the 6th reciprocal meters. Now, hopefully that reciprocal meter is going to be enough to remind you that this is not the correct answer, but I get a whole lot of students that leave it here. You've got to remember to get the reciprocal of this. So 1 over this value, 1 divided by this value, we get a wavelength of 4.86 times 10 to the negative 7th meters. It did ask for this in nanometers, so reminding ourselves that nano is 10 to the minus 9th, we end up with a value for nanometers of 4.86 times 10 to the 2nd nanometers, 486 nanometers. Now the next question asks us what region of the electromagnetic spectrum this is. If we Google this, there are electromagnetic spectrums that show this information, or I simply Googled 486 nanometers and it came up that the color was right at green. It was kind of the break off between green and blue, but it's more in the green range, so it is in the visible light range of green. To which series of the electronic transitions in the hydrogen atom does this wavelength belong? Keep in mind, if it's green, if it's in visible light, so think of our little mnemonic device. If we've got IP very blue urine lately, 321, then first of all, without even doing this problem, since it told us to hop down to the 2nd energy level, we should be able to get it, even if we didn't know at that point that it was visible light. But again, if we know this little mnemonic device, we can get all of that information without even doing the mathematical problem. But we notice that it is in the Balmer series. All the hops down to 2 are visible, and they're called the Balmer series. So that's how we get wavelength. So how do we get energy? Well, in the hydrogen atom, the energy of an electron at a specific energy level can be calculated using these equations. Generally, I would say we most often use this one just because it's a little quicker to use. But most of the time, we're not worried about finding the energy at a particular energy level. We're usually asked to find the energy in the transition. So let's look at a simple problem. If it's a transition, then we're talking about, again, final minus initial for our electron hop. So, example, the Paschen series of lines in the hydrogen atom occurs in the infrared region. We should know that if we know our IP very blue urine lately 321 little mnemonic device. We know what the Paschen series is. So infrared hops down to 3. The electrons that produce them are moving from higher states, as it says, to n equals 3. Give the initial energy level for the least energetic line of the series. Now keep in mind, all of them are hopping down to 3. They're getting smaller and smaller as we go up. But it wants the lowest energy of that series. So if we're talking about this one, this one, this one, and this one, then the lowest energy is going to be the least amount of distance, if you will, traveled. So it's going to be the hop from 4 down to 3. So the least energetic line, the initial energy level, is going to be 4. So what is the energy involved in this least energetic transition? Well, we've just set up here that change in energy is negative 2.178 times 10 to the negative 18th joules times the quantity 1 over the final energy level squared minus 1 over the initial energy level squared. And we've already established that the final in the Paschen series is always going to be 3, so 1 over 3 squared. And the initial we said had to be 4, minus 1 over 4 squared, so 1 over 9 minus 1 over 16 multiplied by that constant. And we get the energy as being negative 1.059 times 10 to the negative 19th joules. Now keep in mind, that energy has to be negative if we're talking about a hop down. Because remember, negative energy simply means that it's being given off. And if we have a hop down by an electron, that's occurring because it's giving off energy. The next thing it asks is what the frequency and wavelength of that light are. Remember, we have an equation for relating energy and frequency, E equals h nu. So if we know the energy and we're trying to find the frequency, our frequency is going to be E over h, which is Planck's constant, remember. The energy we just established was 1.059 times 10 to the negative 19th joules. We're going to divide that by Planck's constant, 6.626 times 10 to the negative 34th. And we can go ahead, we've used different units for Planck's constant in the past, but the simplest units, joule seconds, will actually work just the way we want them to in this situation. Joules are going to cancel, and we're going to be left with 1.598 times 10 to the 14th reciprocal seconds. And remind yourselves that reciprocal seconds are hertz is the common unit for that. So that's going to get us our frequency. And now if we want the wavelength, we can use the equation E equals hc over lambda to get our relationship between energy and wavelength. So wavelength is going to be hc over energy. Again, Planck's constant, 6.626 times 10 to the negative 34th joule seconds, times c, which is the speed of light, 3.00 times 10 to the 8th meters per second, divided by the energy we just found up there, which was 1.059 times 10 to the negative 19th joules. And when we calculate that, we end up with 1.876 times 10 to the negative 6th meters. As you can see, our units cancel, joules and seconds, we're left with meters. So a valid unit for wavelength, and that is our answer.